Hey guys, welcome to my channel. In this video, we are going to talk about how to determine pKa value without calculation. First, let's review what is Ka. So Ka is the molarity of proton in an aqueous solution times the molarity of ionized form of a weak acid divided by the molarity of the weak acid in the aqueous solution. So if the K value is bigger, means more weak acid is dissociated into the proton and ion. First, let's talk about the strength of binary acids. So in the case of binary acid, we consider the bond dissociation energy. So if we want to dissociate the HX bond, we need energy. So when comparing binary acids of elements in the same row of the periodic table, acid strength increases as the polarity of the bond increases. When comparing binary acids of elements in the same group of the periodic table, acid strength increases as the length of the bond increases. So let's explain why this happens. So when we look at the elements in the same period, as the atomic number of the central atom increases, the electronegativity of the atom increases. So it's more likely for the central atom to stabilize the electrons around itself. So the shared electron pairs within the HX bond is getting closer to the central atom. So as the atomic number increases and the electronegativity increases, the proton is more likely to lose. In other words, the HX bond is more likely to be dissociated. So the bond dissociation energy is decreasing. Okay. So when we consider the elements in the same group, instead of considering the atomic number, we consider the atomic radius. In other words, the bond length. So from top to bottom, the bond length increases. So the distance between the proton and the nucleus is getting bigger and bigger. So the bond dissociation energy is becoming weaker. So the bond is more likely to be dissociated. So the K value is increasing. Okay. Then let's talk about the oxo acid. In this case, the central atom is oxygen, and we attach halogen atom to the oxygen. In this case, we consider the electronegativity. So chloride and bromide are in the same group. Chloride is slightly more electronegative than the bromide, which means chloride is more able to withdraw electrons. So the electron pairs within the HO bond, the shared electron pairs is getting closer to the oxygen side. So the proton is more likely to lose, so the K value is bigger. So when we comes to the species like this, instead of consider the electron activity and the central atom, we consider the terminal oxygen. So the terminal oxygen is electron withdrawing. So when we have more terminal oxygens, the terminal oxygens is withdrawing the electrons from the shared electron pairs within the HO bond. So the proton is more likely to lose. So in this case, the sulfuric acid has 2 terminal oxygens, has only 1. So the one on the left is a stronger acid. Then we talk about the strength of an organic acid. So we consider the acetic acid and ethanol. In this case, we consider the resonance structures. Because of the resonance structure here, it is more likely to stabilize the electron pairs than the one without resonance structure. So let's review the 5 patterns of the resonance structures. First one, allylic lone pair, a lone pair and a double bond. Allylic positive charge and double bond. Lone pair adjacent to positive charge. Okay, pi bond between 2 atoms of differing electron activity, and conjugated pi bonds. So you have to memorize these 5 patterns. And then, if the carbon chain is longer in the organic acid, the K value is going to be smaller because carbon atom is an electron donating group. It's not an electron withdrawing group, it's an electron donating group. So the proton is less likely to lose. But when we add hydrogen atom, in this case a chloride, to the adjacent carbon, since chloride is an electron withdrawing group, so they withdraw the shared pair electrons within the OH bond closer to the oxygen side, so the proton is more likely to lose. Therefore, the K value is bigger. Okay, let's do a review question. Which acid is stronger? We look at the first pair, the phosphorus and chloride. These are the central atoms of the 2 species. So first we consider the central atom. So the electron activity of the central atom of chloride is stronger than phosphorus. Okay. And we consider the terminal oxygen. In this case, the one on the right has 2 terminal oxygens. So obviously, this one is a stronger acid. And then we compare the second pair. So the chloride is closer to the proton. So since chloride is an electron withdrawing group, and we add chloride to the adjacent carbon. So the chloride withdrawing the shared electron pairs within the OH bond, and the proton is more likely to lose. So the one on the right is a stronger acid. Okay, let's talk about amines as bases. First, we consider the ammonia and bromamine. Since bromide is an electron withdrawing group, so it will stabilize the electron around the nitrogen. And so it's less likely for the nitrogen here to donate electron pairs to grab a proton. So the bromamine is a weaker base, okay? Because it is less likely to donate electron pairs. So this one, bromamine, is weaker base than ammonia. And then we consider the length of the carbon chain. As we said in the previous slide, carbon is an electron donating group. So if we add more carbon to this species, in other words, carbon chain is longer, the electron donating effect is stronger. So it is more likely for the nitrogen here to donate electrons to grab a proton. Okay, so the species which has a longer carbon chain makes the stronger base. So if we have a resonance structures here, so as we all know, the resonance structure is going to stabilize the electron pairs, make it a weaker base. So when we consider the species with the resonance structure and without the resonance structure, obviously species with the resonance structure make it a weaker base, because it's gonna stabilize the negative charge, make it unlikely to donate electron pairs to grab a proton. And when we consider the other atom being added to the ring, so if it's getting closer to the amine, so the electron withdrawing effect is stronger. So since the chloride is added right onto the adjacent carbon, so the electron withdrawing effect is stronger. So it's likely for the amine group to donate electron to grab a proton, so make it a weaker base. Let's do a question. So the K value is stronger or weaker? The base is stronger or weaker? The pK is larger or smaller? Because we add chloride to the adjacent, like carbon. Since chloride is an electron withdrawing group, so it's gonna withdrawing the electron pairs within the OH bond. So it's less likely for the electron pairs to be donated to grab a proton. So the Ka value, the pK value, is gonna be smaller. Let's do a question. So which pK value is incorrect? So the answer is this one. So amino group of adenine. This one is incorrect. This is not 9. Okay. Let's say why this happened. So pay attention. This is pKa, not pKb. Okay, pKa. So this one should be smaller because it has a resonance structure here, a conjugated double bond. So when we are given this type of question, we are given the pK value of all the amino acid. So when we consider the structure of amino acid, the amine group, right? But the amine group usually do not have a resonance structure here. So it's around 9. But in this question, we have resonance structure here is going to withdraw the electrons from the NH bond. So the proton is more likely to lose. So pKi value should be smaller. Okay, that's all for today.